Trig Ratios. These are very famous. Famously known as SOH CAH TOA. Okay? It's a mnemonic that tells you that S for sine of theta or sine of x, a function on the angle theta, which is equivalent, I should say, to the ratio of the opposite side to the hypotenuse side. So to say what that means real quick, so if we have this right triangle right here, this is all going to pertain to right triangles. So we're starting off with right triangles, then we'll expand to more triangles. So if you have A, B, C, or I like to do it with numbers because some people, the letters are crazy, spooky, but it will come in time. Being comfortable with just seeing variables. It took me a good minute, but then when it finally happened, it was very satisfying. I remember every time a professor would write down like a general version of what we were doing, I would just roll my eyes or throw my hands up. It was like, oh, look at all these letters, look at all these symbols, like, why is this important? But it's important because the point is to understand the general form, and then you can apply it to specific applications. So for example, this is the general form, and then specific applications would be like 3, 4, and then what's this, So Pythagorean theorem is a squared plus b squared equals c squared. It's a general equation for any set of 3 sides of a right triangle. And then a specific application is if you happen to have a real life plank, right? You have a plank that's 3 centimeters long. That's a really small plank. A 3-foot plank, a 4-foot plank, right? Made out of real life wood. Well, then, if you're like, oh, well, we need to connect this with a board, what's the length of this board going to be? If we want it to perfectly connect these two, we can only get one shot at cutting the wood, so we have to measure it and cut it. Well, then you do the Pythagorean theorem on these, which this is feet, right? It's going to equal 3 squared plus 4 squared will be 9 plus 16, so it's going to equal 25. Right, this is square feet as well. And then, so that's a squared plus b squared equals c squared. We want to know just c, because it's just this length of this plank is just c. So then we have to take the square root of this. So the square root of 25 square feet is going to be, right, 5, and then just feet. So the square root of square feet is just feet. So it's a classic 3, 4, 5 triangle, which we love. Anyway, so the general form is what we care about. When you talk about opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, well, it's with respect to the angle. If I bring this here and we transpose it sort of onto a circle, which in trig we're usually dealing with triangles and circles. So this is that horizontal we spoke about before. This is 0 pi. This is, we don't know yet. And let's just put this triangle right here. Right? Here's the horizontal. Then this is pi over 2. So we have a side length of A, a side length of B, and then a side length of C. So when it's there, it becomes apparent that the angle we want to deal with is this angle. So again, I just write this little square to say it's a right triangle. That's a right angle right there. But really, this is the angle that we care about a lot of the times in like introductory truth. It gets more interesting when you have to flip that triangle around to try to make it make sense for your specific application. But for now, let's work with this. So we have, so is sine of the angle is equal to the opposite, right, over the hypotenuse. So that says that the sine function performed on theta is equal to the ratio of the opposite side. So the side that's opposite of the angle. So we see that our vertex is here. Focus on this angle. The side opposite of the angle is over here, this so that's B. So then we have opposite B. This adjacent side is adjacent to the angle because it's right here. It's close. This side is opposite the angle we're focusing on. And then the hypotenuse is that, again, the interesting result of the Pythagorean theorem over here that we often care about. Opposite of our hypotenuse is going to be B over C. All that this says is the function sine performed on the angle theta results in the ratio of the side opposite to theta over the hypotenuse side, which we have as green. So the function sine performed on the angle theta results in the ratio of the side opposite of theta over the hypotenuse side with respect to theta. This means with respect to. It's very useful shorthand. Okay, and so this is a lot of words, mumbo jumbo. So we like to say, so sine, opposite, hypotenuse. Or sometimes it's written as just over h. So there we go. We can move on to the next function. It's the same idea. The COS is cosine. So people say cos. Cosine of the angle is the adjacent side over the hypotenuse. So the ratio of, quickly, if we're focused on this theta, which we often are, again, because you can imagine a circle that this is in, for that triangle, we have cosine of theta is equal to the adjacent side over the hypotenuse. So cosine of theta is going to be equal to the adjacent side over the hypotenuse, which just says that the cosine function performed on this angle theta, this one, gives the ratio or fraction adjacent side over hypotenuse side, which is 3 over 5. And the last one is tangent on theta gives opposite over adjacent. You might realize that's a little different, that's weird. The other two have been with the hypotenuse in the denominator. So if we have this, the tangent is this opposite over the adjacent. So tan here is B over A. And then reciprocal trig functions, also strangely daunting at times. But it's just 1 over a specific trig function, one of the basic ones. It's just flipping it. And you will learn too to be very comfortable as you become a powerful physicist or mathematician or chemist or biologist or computer scientist. You will be more comfortable with things like 1 over sine of theta being, sine of theta to the minus 1 power. What did we determine was sine of theta earlier? Remember? We said sine theta is equal to so OH, right? you'll get comfortable with just saying, okay, so what's 1 over the fraction OH? It's a flip. You're flipping a fraction, so it's just H over O, right? And if you happen to see this, it's also not scary. Don't be afraid of that. It means this. That's it. You're just flipping sine upside down. So let's see, secant is 1 over cos, right? 1 over cos, which again is equal to 1 over, so ka is AH, so 1 over A over H. Fractions like this look goofy, but it's just 1 over something is the thing that is you're saying it about flipped. So if I say like 1 over, smiley face divided by donut, okay? Donut. That's a delicious donut. 1 over smiley face divided by donut, or 1 over smiley face over donut ratio is just donut. You just do this. So pop up. If you have a remarkable tablet, just do that. This would still be a smiley face. Okay? Smiley face over donut to the minus 1 power. It's just donut over smiley face. Don't be intimidated by that. So don't be intimidated by reciprocal trig ratios. So cotangent is the last one. It just, obviously, it sounds like it's 1 over tangent to me. So we're going to write 1 over tangent of theta. Every time you write any trig function, again, don't get sloppy and write this. I've done it a lot, but it's a function. Tangent doesn't mean anything without a theta. It needs to be always recognized to carry that down when you're working, that you're doing work on a certain angle. Theta should always be there. If you're writing a trig function, you're writing an angle. Sometimes it's written as x. So you'll see any of these, oops, right? All those mean the same thing. It's just if you put the x here and you said the angle is an x, the variable doesn't matter. You could, as you go on, you might see this, just know that it's some angle. You might see this. Just know that it's some angle alpha. Okay. So that was a little tangent, which is very fitting. But cotangent is 1 over tangent. We know that tangent is TOA, so we have up here, we'll put it as a note. Another quick tip is that you are more than welcome, and your teacher will never, your professor, your teacher, whatever level you're at, they're never going to take points off or condemn you for doodling or writing notes anywhere on your test, your quiz, your homework. So if you just write TOA there, you know, I've literally been doing trig for like 8 years, 7 years, I don't know. And I write TOA there just obviously because I'm doing these notes, but it's nice. Like sometimes I'll even put put your finger here while you're doing it in your brain. Take a little note. Put one finger on the TOA and one finger on the thing you're working on. Again, it might not be that necessary of a mnemonic for trig. Like after this lesson, you should get 100%. Should be easy. But things get harder in math. But you can almost put your finger on there and put your finger there and just help your brain add that information to the flow. I'm on exams too in a trig class. I'm constantly drawing, you know, this. Oh, you have it on there. This little, something on the side that says, okay, how much is this? Okay, that's pi over 2. Doodling all over your test is not going to make you lose points. It's probably going to get you a way higher grade. That's why we ox the final answer at the end. Because the professor knows, this is some of the hardest content to be worked on. So they can do whatever they want on the page as long as the box is around their final answer at the end. Or if you do proofs, it's this or this. But that was a tangent. On top of a tangent, you might call it a cotangent, but not definitionally. because cotangent is, what was I writing? Cotangent equals 1 over tangent, right? Which TOA equals opposite over adjacent flipped. Oops, there. Nothing I wrote was false, see, because I added this. This is true. Another quick aside, this isn't a tangent, this is an aside. A lot of times, this will actually all be written in x and y's, because this is an x coordinate, and this is a y coordinate. Just when you're working in the x and y, I mean, I'm using op and adjacent and ABC because the Pythagorean theorem is known for this. So tan of theta equals y over x. Yeah, it'll be written like that. And then cotangent be like that. So you can quickly, put together, okay, tangent is y over x, cotangent is x over y, cosine is x over r, right? Adjacent over hypotenuse, yeah. X over r. And then secant, which is 1 over cos, is r over x. Then you have, right, sine is y over r, cosecant is r over y, because it's 1 over sine. Good. Okay, another thing I have in my notes is okay, so if you're given two sides of the right triangle, which you can just sort of write like this, my right triangles are so bad today. Given two sides, then you just use Pythagorean theorem. So if you're given this, again, this is the general form. This is right triangle. General form. And you're given this 3, 4, and then we don't know c. Then you do a squared plus b squared equals c squared. Then you take this 9, this 16. This part could trip you up too, but you just have to think about it for a second. Remember that c squared is equal to 25 in this case. So if you want to know c at the end of the day, now you do square root of 25 equals c, which equals 5, right? Then if you're given one side and the angle, so in a different case, you're given this 30 degrees and only this side, right? You can solve that. So we'll say this is B and this is C. We can do, this is going to get mathy, as it inevitably does. If you have, so A equals 3, then you know something like sine of theta is opposite over hypotenuse. So B over C. Are we going to use the sine function to give us more information? Probably not. We know this, but these are both variables, so there's nothing we can do with it. So we won't use it. Cosine of the angle is going to be equal to pi adjacent over hypotenuse. So we have 3 over c. Now we have enough information to solve for c. So we'll do cosine of 30 degrees. It's going to be, what? Square root of 3 over 2. Cosine of 30 degrees is equal to this number, is equal to 3 over 2, right? And then I also say that this is true. So if I know that this equals this and this equals this, then we know that this equals this, right? Because if cosine of 30 degrees is equal to root 3 over 2, and cosine of 30 degrees is equal to 3 over c, then root 3 over 2 is equal to 3 over c. So now we do algebra time. What we're about to do is algebra, which is so much fun. Everybody loves algebra. if you have fractions across an equal sign, I always take the easy route. So my first thought is, say I'm going to take this c and multiply it over here, but I want the c. So instead, I'm going to divide by the 3, which means I'm going to multiply it down here, And I'll do that step by step. I'll do it the quick way, but then I'll do it step by step. So in my head, it goes, okay, this 3 goes down here because I want this c, which means 3, 2 times 3, okay, equals, and then we have to leave this like this. Which again, remember, this is the same as this. See, I don't need the parentheses probably. Okay, that's a quick aside, but so that tells me that root 3 over 6 equals 1 over c. And the way reciprocals work, the way you can flip fractions all the time, is you can say, okay, well, if this equals to 1 over c, then flipping this to 6 over root 3 will allow me to flip this to c over 1, which we don't have to write c over 1, we can just write c. So c is 6 over root 3, and that's your answer. If we were looking for c. So, what did I say, 6 over root 3? Sure. Okay, which is just some weird number. Again, it looks crazy, but and I'm working on getting my calculator hooked up. Anyway, the professor will say, "Oh, it's just a number at the end of the day. Don't worry." There's your answer. 3.46 something. But anyway, for this algebra, I wanted to do it a little more slowly. So the a little more sense making on this algebra is that if you're left with this, again, no shame in writing out as many steps as you need or want or just feel. If I want c alone, then I'm going to write 3 over 2. So the thing on the top is being multiplied, and the thing on the bottom is being divided by, right? So what you have here is, in another way, you can say it's 1 times 3, right? All divided by c. It's weird to write it like that, but that's how that's, again, you can make sense out of these things, and it becomes easier and fun. This is basically the right side it has a multiple of 3 and a divisor of c. So if I want the 3 to move to the opposite side of the equal sign, then it needs to do the opposite operation over here. The way that this is taught in an algebra class, or at least in my day, was to say, okay, we're going to do divide by 3 on this side, which a divided by 3 is the same as a times 1/3. A is for arbitrary, so don't look into it. But what we can do is, multiply by 1/3 on both sides, or divide by 3, whatever you want to call it. And so the step-by-step way of doing this is, okay, so 1/3 times root 3 over 2 equals 1/3 times 3 over c. And then here we'll have multiplication, which is easy to do. So multiplication, you multiply these, the denominators together, you multiply the numerators together. Okay, same here. 3c. Okay, then these 3's cancel. Or an easy way, the fast way would just be say, okay, that's 1 over c, right? But I'm doing it this way to be as clear as possible. So when these cancel, now we'll have this, which is where we were in my other demonstration of it. So again, 1 over c equals root 3 over 6. Okay, so now, if this is true, then as long as you do the same operation on both sides, right, that's true. So arbitrary to the -1, remember, is the same as 1 over arbitrary, whatever this is. So if I do that, then I'm going to do flip. I'm going to do flip. I'm going to do get rid of this unnecessary 1. And now I have my answer, which this is approximately 3.4641. So inverse trig functions are useful if you have the sides and you need the angle. This part also sort of, I think, tripped me up back in the day. Oops, TOA, that's funny. Opposite over adjacent, that's the OA. So these were sort of weird to understand at first, but again, we're going to go through it very practically, so it makes sense. So in the demonstration, the examples I've given so far, case one is known, known, unknown, right? And this could be any two, it could be this one's known and this is unknown, or this one's, this one's the unknown. If you have this case, if you have either number unknown, or you have you just use Pythagorean theorem. Okay, then next case, so this is case one right here. Okay, how to do a lecture on this. So case two is we know we have an angle and we have a number, and then boom boom, we have, okay, in all of these cases, this is what trig functions are for. Normal trig functions, which is sine theta equals there's a third case, and that is why we need inverse trig functions. So in the third case, you have no known angle, but you have at least two sides. So you have a number here, a number here, even if this is an unknown. And normally the way this occurs is you're going through a practical problem, you're going through a problem. It's not going to be laid out like this. I mean, it may be in really introductory lessons, it'll just say, can you find this angle theta? But the way I've experienced it, it's mostly you're doing a practical problem, some sort of problem, whether it's a physical phenomenon, math things. You will you will come to a point where you realize, like, oh, it's the angle that I need, or you're like going through the problem, you're doing this, you have this, you have like an angle here, you have sides, right? You have this rectangle, then you're like, oh, like, okay, this is a right angle, this isn't these, so this is true, this is not. You're doing this, and then you get to a point where you're like, oh, I know this. Um, it's the theta that I don't know. Right? So in that case, you need inverse trig function, which comes across as scary, but all it says is if you do the inverse of sine on the thing we learned, then you get theta out. Cosine of, what am I doing? Adjacent over hypotenuse will give you the theta. Inverse tangent, opposite adjacent, opposite over adjacent will give you the theta. It has to be clear that sine of theta is opposite over hypotenuse, or y over r, depending how you're looking at this. So remember, you have this triangle, opposite over hypotenuse, or the distance right here is actually y, and the distance here is x, right? And the distance here is r. So however it's written, the sine of theta gives you a ratio of sides. So sine function on an angle, whether it's in degrees or radians, gives the result of a ratio of sides of the triangle, of a right triangle. Whereas the inverse sine function has to be performed on the ratio of sides, and the result is an angle. So, and I'll write this, right? So this inverse trig function, inverse sine function, takes in a ratio of sides. This and gives us, as a result, an angle, whether it's in degrees or radians, okay? This regular sine function, remember, takes in an angle, and then the result is a ratio of sides, okay? It's gonna be key, and it's gonna be hard not to mess that up, but sometimes, if you find yourself doing this, inverse sine of 30 degrees equals that. If you see this happening, you already know the answer is not 0. The answer is not going to be incorrect. The answer is no solution, right? That's not. You are bastardizing the function. You're not allowed to do it. The function doesn't do that. Inverse sine doesn't take angles in the first place, so it won't give you any result. Okay, so I'm going to do some problems. Remember, on our unit circle, this would be theta, but we're doing they're making it more interesting, right? So what I like to do is, for this triangle, let's make it interesting, or, less interesting, actually, right? We'll rotate it this way, 90 degrees. This is optional, you don't have to do this, it's just, again, like, we associate in our mind eventually when you have done enough trig, you associate all the triangles being like this, right? Where the angle is over here and it's this angle. Alpha is easier to draw. It's this angle, so then this is the triangle. So I rotate it to make life easier. And I mean, another aside or a tangent while we're working on trig is, I can't tell you how many times the professor said, we're going to do this extra step, which is more work, because you see I'm sitting here drawing a triangle. It's more work because it's going to make life easier. It's delayed gratification. You're doing work now for a simpler task later. And it's a trade-off. You could leave the triangle like this, and I can, just think with my head on the side. Or, of course, you can look at, opposite. You can say this must be adjacent, and then this is the hypotenuse. You can work like that. It's optional to switch it like this. But, yeah, let's solve it. So here's my triangle. I'm going to say I don't have the opposite. I do have the adjacent, and I have the hypotenuse. So we have the adjacent of hypotenuse. Put the C here. We have CA. So that's cosine we're going to benefit from. Cosine of theta is adjacent over hypotenuse. That's equal to 1/2. You can quickly do this. So cosine, we now have 1/2. Secant is 1 over cosine. Never forget, right? Secant is 2. Easy. What else do we have? So we have now cosine. This is a good example of when we can use Pythagorean Theorem for a little bit of help. So I want to know sine of theta, but sine requires opposite over hypotenuse. So b over 4, sine of theta is b over 4. We don't know what theta is, so we're kind of stuck. What we can do is say, okay, a squared plus b squared equals c squared. Okay, thank you. This is Pythagorean theorem. So 4 plus b squared is 16. Then it's algebra time. We'll do minus 4. Minus 4 minus 4. So we have b squared equals 12. b equals plus or minus the square root of 12. But we're working with a triangle that we presume exists, and all of the sides are real length, so they're positive, so we can just drop this. We don't have any negative length triangle sides. Equals the square root of 12, which is the square root of 4 times the square root of 3, which is 2 root 3, okay? So our b here is the quite peculiar 2 root 3. What was c? 4. Okay. And now that we have that filled out, b equals 2 root 3. Now, I'm going to erase all this. That was just to find our bonus side so we could get the rest of the trig function solved. All right. And so we have now our newfound b, which is useful, 2 root 3. So now sine is equal to, sine of theta is equal to opposite, which is b, over hypotenuse, which is 4. This 2 and this 4 cancel into 1/2. 1/2 of root 3, or root 3 over 2. Okay, and then we'll just do the inverses quickly because it's convenient. Cosecant is 1 over sine of theta. Sine of theta is this. So cosecant is 2 over root 3. All right. Tangent is sine over cosine, and sine is this. Cosine is this. To solve that, we'll do root 3 over 2 divided by 1 over 2 is the same as root 3 over 2 times 2 over 1, which is a fun trick. Useful at times. All right, so this is going to be square root of 3 times 2, which you can only write as that, and then 2 on the bottom. 2 over 2 cancels. Since these are being multiplied together, you're allowed to do that. So your answer is root 3 for tangent. And cotangent, you guessed it, 1 over that, right? Goes there. Cotangent is 1 over tangent. Okay, good stuff. Let's do this one. Again, I'm going to do it quickly to show you that it's not too scary to do. Redraw this triangle the way that I feel comfortable looking at triangles. Theta to root 5 on the hypotenuse. And this is A, this is B, this is C. Off the bat, then we're going to do Pythagorean Theorem to get 2 squared plus B squared equals root 5 squared. This is 4, this is b squared, this is 5. These cancel, that and that cancel. Then it's algebra time. Okay, subtract this 4, put it over here, minus 4 here, minus 4 here. We have b squared is equal to 1. Therefore, b is equal to 1. Okay, again, it's plus or minus 1, but it's a triangle. I mean, negative sides on a triangle, you're getting speculative. Okay, so it has to be positive, so now we know our b is 1. Cool. Tracing the Pythagorean theorem, you know it, okay. Now let's just go. So sine is opposite over hypotenuse, 1 over root 5. Cosine is adjacent over hypotenuse, 2 over root 5. Tangent is opposite over adjacent, so 1 over 2. Cosecant, I always, in my head, I'm thinking, okay, sine, because I pair it with that, right? If you solve them in this order on your homework, or like I said, do sine and then cosecant right away, it's just that it's solved, right? Your cosecant, all the inverse trig functions, which at first are like, oh, there's 6. There's only 3. There's 3 and then they're inverse. And like I discussed earlier, inverses are free. It's fun. So, sine, we know that's 1 over, sorry, I almost said 1 over cosecant because it's true. Sine is 1 over cosecant, cosecant is 1 over sine. So, I'm thinking sine in my head here. That's what that arrow means. Cosecant is this flipped upside down. I'm not going to write the over 1 this time. Secant is this flipped upside down. And then cotangent tangent flipped upside down, 2. Easy. Alright, so we're going to use identities to find the exact value of each of the 4 remaining trig functions. Okay, so they gave us sine and cosine and told us sine is equal to 1/2 and cosine is equal to root 3 over 2. Well, you can deduce then from that since sine is opposite over hypotenuse, then the opposite angle over here is 1. Sorry, the opposite side opposite the angle. And the hypotenuse is 2. And then cosine tells us, again, another way to write it, cosine tells us r over, x over r. We've already deduced here that r is 2, x is root 3. So there's your triangle. So they gave us sine cosine. We need tangent, which is opposite over adjacent. We need cotangent, which is adjacent over opposite. We need cosecant, which is 1 over sine, so 2. And we need secant, which is 1 over cosine. So we flip, which is 2 over root 3. Okay, same goes for this. Here's the triangle. Sum theta. Sum r cosine of theta down here. Sum r sine of theta here. And some r here. So let's see, sine is this. That means sine is y over r. So y equals root 3. R equals 2. And it gives us cosine. So cosine is x over r. X is 1. There's the triangle. 1, 2, 3 over 2. Okay. So we'll do the easy ones again. Cosecant. It's 1 over sine theta. So the flip of that. Secant. It's 1 over cosine. So 2. Tangent is y over x or sine over cosine. However you want to look at it. That answer will be sine over cosine. What's my sine? Sine is root 3 over 2. Okay. My cosine is 1 over 2. So a number on top in the numerator divided by a number on the bottom in the denominator is the same as, if you have both fractions, is the same as this, right? Root 3 over 2 divided by 1 over 2 is the same as root 3 over 2 times 2 over 1. And I'm out of room, but we'll just cancel these. And root 3 over 1 here is just root 3. So that's the tangent. And then last thing is cotangent, which, spoiler, that's tangent. Cool. Moving on. And so 7 here. So we're going to build our triangle. Sine of theta is 2 over 3. So it's 2 over 3. Cosine of theta is root 5 over 3. So it's root 5 on the adjacent side over 3. Hypotenuse. Cool. We have the triangle. Easy. Cosecant. Okay. We're going to put down here 1 over this. So 1 over 2/3 is 3/2. Secant. We're going to take cosine. Put it right down here. 1 over root 5 over 3. 1 over root 5 over 3 is 3 over root 5. Okay, last one's tangent and cotangent. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. Okay, beautiful. And then what's this one say? Use the definition or identity to find the exact value of each of the remaining 5 trig functions of the acute angle theta. So I noticed this when I was writing it over. When it says acute angle, the reason it's saying that, this is somewhat important, I'd say. It's specifically telling you acute angle theta because, where is it? It's around here somewhere, 1, 2, yeah, it's around here. This value, when the angle is this theta, which is 45 degrees, spoilers, This value you'll also get if you were to go around the circle all the way and continue back to here, which would be 45 degrees on top of a whole rotation, right? So if you did sine of 405, you're also going to get this. So that's the reason they say there's detailing that just to let you know, don't get crazy with it and find and work as if it's 405 degrees. Because again, it'll do the same thing. If you then go around again, your sine of what's 360, what 765? Your sine of that is also not 3, sorry, 2, root 2 of 2. So yeah, tangent, but that's what we're here for, is trig. So anyway, there's also several ways to do this one. Again, this tells us two sides of a triangle. I don't think you'll be in trouble for solving it one way versus another on an exam or something, because I think they don't really care if you get the right answer. But this tells me opposite over hypotenuse, so opposite over hypotenuse. You might say, well, what's that last coordinate? Well, it's x squared plus this squared equals this side, right? There's x, there's y, we already know y. Pythagorean theorem, you can write it like that. This is just the general form to write it. We often use this when you're talking about something that exists, right? This is the radius of the circle. The radius is this much. It's the same no matter where you point. And then the angle, or sorry, then, this radius of this circle, and then this triangle that's created, this right triangle that's created here, you have x, y, because when you're looking at the circle on a 2D plot like this distance is x, this is y, this is r. The radius of the circle, it touches the circle. X is the distance over and the distance up to get to y. Okay. So anyway, this is the same as a squared plus b squared equals c squared. We have x squared plus y squared equals r squared. So x squared plus 2 equals 4. Take this from over here. So we have x squared equals 2. So we have x equals, to have good form, we should write plus or minus 2. But remember, on a triangle, a negative number, it doesn't really make sense because it's, a shape. You're measuring a shape. Where do you get off saying, oh, it's a negative distance from here to here on the shape? You can't. So x is 2 then. So again, I don't know. This 2. Did I do that now? X is 2, so 4 plus x squared plus 2. 4 minus 2 is 2 x. Oh, okay, we're gonna have to cut that out. Chop, chop, chop. All right, and so x squared plus, this is just gonna be 2, this is gonna be 4. Take that 2 away, then you're gonna have this, right? And then technically to have good form, we would write plus or minus root 2. But again, negative numbers on a triangle don't make a lot of sense because what you're saying is the distance from here to here is something. The distance is negative, doesn't really make sense. So we don't have to write that. So this is our triangle, root 2, root 2. This is a quick check too. You can tell that this makes sense because if you have a leg here that's root 2, square it. You have a leg here that's root 2, and you square it. Well, okay, then you have 2 plus 2. To get this number, you take the root of that, so it's 2. Might cut that little bit that was in the side, that's pointless. And then that's it. You can just write the rest. Cosine is adjacent over hypotenuse. Tangent is 1 because it's this over this. And that always rings true to me that tangent of theta. I know what the angle theta is too. It should be 45 degrees. Did I write that somewhere? I know, oops, where we go? I know that whenever I see that the tangent is 1, it sort of just triggers something in my mind. Like it's just known that this line talking about that this angle is 45 degrees or pi over 4 because, bear with me, so the tangent defined as sine over cosine, right? It's 1 because it's saying that the sine and the cosine are the same value, right? Which results anything that's over itself is going to give us 1. So here in this situation, you're thinking which triangle is being made when this angle is 45 degrees. Well, it would be good to draw this one to scale to really send it home. And I mean, I didn't do great, but it's pretty decent. We're saying that the legs of the triangle here are the same length, x and y, okay? Which, again, makes sense about this triangle made out of 45-degree angle because, you can have different triangles. You can have this really shallow one. You should look at it this way. This blown up over here is a shallow angle on the triangle, a short y, and a long x. You should expect that the ratio of y to x, right, if y is smaller than x, this is going to be a small number. And then if you have a triangle made out of this, right, out of this angle, whatever it may be, then you have this triangle where x is small and y is large. So then the tangent there, which is y over x, is going to be larger because y is the bigger piece, big over small. And then when you're in this circumstance right here, where it's 45 degrees, pi over 4, it's cutting this arc in half, it's going to create two lengths, a triangle with two legs that are the exact same size, x is equal to y. On the unit circle, you'll also see the coordinate of the x here at 45 degrees. The x coordinate is root 2 over 2. The y coordinate is root 2 over 2. So tangent is root 2 over 2 over root 2 over 2, which is 1. I hope that helps a little bit. It's not necessarily pivotal. It's just like, again, a way to look at the pieces of the puzzle to make things intuitive instead of memorization and this thing. I don't know if I mentioned it before, but this I would go my exam. I would go 1, 2, 3, 3, 2, 1, and I mean if you are desperate. So this is essentially a way to write the coordinates 1 over 2, comma. You do the 3 over 2, but then you put the little root 2 over 2, and then you add over 2 to everything, right? Just add over 2 to everything. A helpful little trick. The same thing here, but root 1 is just 1, so we don't actually write the root. And same goes for then this way. The x coordinates are going to match sort of here. So boom, 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 like this. You do the same thing where you go down 1, 2, 3, and then this is the unit circle, by the way. Before I go into these other ones, which are important, again, notice, right, that it's fun and interesting. It's a puzzle. This is a distance of 1/2. See, it's small. And then there's a triangle, a hypothetical triangle here, which I didn't draw the circle perfectly, but it would be more like this, okay? The y coordinate, is root 3 over 2, which you don't have an intuitive sense of how big root 3 over 2 is, but it's bigger than 1/2. Okay, so this bigger number is making up the height of this tall triangle, and then x is 1/2 short distance. The next x is over here at root 2 over 2. This root 2 over 2 is 0.7071 something, right? So you have 1/2, which is 0.5, root 2 over 2, which is 0.7071, and then over here, the long leg x, this hypothetical triangle, right, goes like that. That's going to have an x of root 3 over 2, which is equal to, right? It makes sense that these are the coordinates. It's some triangle that this angle is 45 degrees, right? When you have that, which is root 2 over 2 in the x direction, and root 2 over 2 in the y direction. I didn't mention, by the way, these are just the common angles of 45 degrees, which is pi over 4. Common angle of 30 degrees, which is pi over 6. And this is a common angle of 60 degrees, which is pi over 3. Down here, it's also going to be the same. If the x is the same distance here, my 30 degrees is off, but this is ideally supposed to be right minus 30 degrees, and minus pi over 6 are there. The x length here, from here to here, are going to be the same for both of these. So that's how you can easily go down and say, okay, this is going to be the same. It's a positive 1.72 or whatever distance across here for the length of the bottom leg of this hypothetical triangle we're drawing. And the y, well, the y-axis is this up and down. So to dip down below the x-axis here is going to be a negative. And again, it's the same length, but in a different direction, right? The negative direction. So x is same length as this 30-degree angle right here. And in the same direction, it's positive. The y, this length right here, is the same as this length, except it's now a negative. This is where we use like negative distance technically, but it's just to say, it's saying if you rotate this way on the circle, right? If you go, or sorry, no, it's not, yeah, it's the same length, but you have to travel downwards. So, if you go below the x-axis, you're now in the negative when you're talking about y's, right? All the y's up here are positive, all the y's down here are negative. Same goes with x. All the x's over here are negative, and all the x's over here are positive, using this as the dividing line. So back to why the unit circle is the way it is. So this is what, negative 30 degrees or negative, whatever you want to call it. This one over here, we're going to call not negative 60. It's a 45. This is a negative 60. And so the x's are all going to remain positive and just copy it from up here. Root 2 over 2, comma, and then the y is going to be the negative version of that, right? This, but negative because it's the same distance, but south instead of north. And then this last one will be the same, positive x, and then the same as this y, but negative. There you go. And we keep going. So from this line, again, these are the practiced ones. If you add 30 degrees to 90, then you're going to have 120 degrees. Technically, it should be like this. I don't know. It's getting kind of sloppy, so I'm gonna just start a new page that looks better, okay? Because I realized I didn't do the unit circle. This is the x direction. This is the y direction. This point, we got our trick here. 1, 2, 3. 3, 2, 1. Okay, then we're gonna go root 1 over 2, root 3 over 2, root 2 over 2, and then square root of 1 is 1, so we leave that out. Remember, this is the x and y coordinate of this point on a circle with radius r equals 1. And as I spoke of before, we will simply keep the same x length, and it's a negative version of the y length. Keep the same x length, which is this, negative version of the y length. Keep the same x, negative version of the y. And then here, cut this in half, okay? This is 90 degrees, or pi over 2. Then this rotation here is 90 plus another 30, we'll call it 120, or 4 pi over 6, which is 2 pi over 3. And so then same rule here is this y is going to be the same. The x is going to be negative 120 plus 30, and then we add another 15, 135 degrees, and add another 15 to be 150 here, or pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and it's this rotation here, and that's going to be negative root 3 over 2, 1 half in the y. What, a negative x and a negative y, right? So we're the negatives for the x, and we're down here, so we're in the negatives for the y, right? So we can even do this, x, y, positive, positive, x, y, negative, positive, x, y, negative, and x, y, positive, negative. And it's complete, except for the fact that I did do this negative rotation here, but as I said before, this rotation is going to give you the same result out of a trig function as, the rotation that goes all the way around here. Rotate all the way to here. This angle, what's this one? 3 pi over 2, or 270 degrees. Which, by the way, the coordinate here is 0, -1. This is 1, 0. This is 0, 1. And this is -1, comma, 0. So anyway, this angle is the tangent of theta is 1. I know what the cotangent of theta is. Also 1. Because it's 1 over 1. Okay, so is that all of them? Cosine, tangent, cotangent. Cosecant is 1 over sine, so 2 over root 2. Secant is 1 over cosine, so 2 over root 2 again. There's a whole other thing where this is actually equal to 1 over root 2, and this might come off as another tangent, but I should actually show this because it can be kind of jarring at first. It's like actually kind of annoying if nobody says it, like nobody points at it and says, look, this is what's happening. This, add a page. So a lot of times you'll get this number in your solution at the end, and it happens to equal this in kind of a weird way. It can be explained as, say you took this, multiply the whole thing by 1, right? You're allowed to do this, that's 1, because, 2 over 2 is 1, x over x is 1. If you do this, you get, what's 2? Root 2 times root 2 is 2. 2 times root 2 is 2 root 2's. You cancel these, and you get 1 over root 2. It's just how it's written. It's mostly written like this as a final solution, but when you're doing your work, when you're working things out, you might get this. And so just a simple thing, like if you get this as your answer and that's the solution in the book, you're actually wrong. Yeah, it's good to explain that. I feel like nobody explains that. We're almost through. Let's just finish strong. So secant of theta is 3. That means
cosine
theta is 1 over 3. And triangle this
cosine
is x over r. So 1 over 3. And Pythagorean Theorem tells us 1 squared plus y squared equals 3 squared. So 1 plus y squared equals 9, y squared equals 8, y equals square root of 8, which equals y is 2 root 2, 2 root 2, meaning sine is opposite hypotenuse is 2 root 2 over 3. You could write that. Yeah, I'd say leave it like that. Cosecant is this flipped upside down. Tangent is this over this. 2 root 2 over 3 over 1 over 3 equals 2 root 2 over 3 times 3 over 1, which equals 6 root 2 over 3, reduces to 2 root 2. Cotangent is going to be this flipped upside down.